Good day. This is a video presentation of a bachelor's degree thesis paper entitled Correlational Approach on Optimization of Plant Microbial Fuel Cell Design for Improved Bioelectricity Generation. I'm Nathaniel De Leon, a graduate of Mapua University, and my thesis advisor is Dr. Ray Pamintuan. A quick introduction about the PMFCs. A PMFC, or the Plant Microbial Fuel Cells, were first introduced back in 2008, claiming that they can produce energy from solar radiation by two principles: rhizodeposition and bioelectricity generation by microorganisms. For the past decade, other variations were developed. Aside from the conventional PMFC, we have the macrophyte MFCs where aquatic plants are used, and we also have the bryophyte MFCs where mosses are used. So the primary drawback of PMFCs are the relatively low power generation and performance degradation in scaled-up systems. The current solution for this is connecting a group of PMFC units in either parallel or in series to increase the output voltage and current. The objective of this study is to identify possible correlational relationships between PMFC design parameters and output parameters, to identify possible routes for scale-up. So this is a theoretical research, meaning no experimental design will be created, and all of my data points will have to come from past research articles. I've included all variations of PMFCs for my initial gathering, and I'm able to collect 50 data points from 20 different articles. So the curve fitting is done through Python. All I needed is to define the model function, and Python will do the rest. Now, a linear model is actually enough for my presentation, but I tested the other models as well and can be seen from my paper. Here I have a scatter plot of the anodic area on the left and the cathodic area on the right, both against the maximum power as reported in the articles. As you can see, there is no discernible model function or curve that can fit this data, and this is where the main problem in my research arises. Majority of the experimental setups in the articles are designed to promote power generation, such as acid treating the electrodes. What this means is that I could have data points where the area of the electrodes is the same for two setups, but the power output is different. We can fix this by cleaning the initial data, but we'll need to define some criteria to identify which data points can stay and which ones should be removed. So the most obvious right now is to remove the data points where the setup is modified to promote outputs, as what we want is just the effect of the varying electrode area to output. Meaning that aside from treated anodes, constructed wetland MFCs are also removed, since the presence of wastewater provides external nutrients that also promotes power output. Now, as we can see here, there is still no discernible function that we can fit the remaining data, meaning we have to refine our data further. Now, since we have removed constructed wetlands MFCs from the data for promoting power generation, we can remove the bryophyte and macrophyte MFCs for the opposite reason. Now, articles have reported that the bryophytes and the macrophyte MFCs have lower power generating capabilities than the conventional PMFC. The growth medium is an important factor to consider as well, as it affects the growth and behavior of the plant and their microbes. Now, as much as possible, I wanted to keep only those that uses natural soil in their design, but I opted to include Hoagland solutions as well, since the nutrients that they offer mimic that of natural soil. Now, as we look at our remaining points, we can already see that we can fit a linear model in the anodic plot, but there is one more criterion that we can consider. So an article from Takenazawa et al. Noted that the high external load showed an unexpected influence on the output parameters. And so, I opted to remove the data points that were subjected to 1 kilo ohm external loads. So I stated here that the external resistance that were considered are between 100 to 600 ohms. Now this is because there are the range of the remaining data points. And also, from the remaining points, the plot for anode area versus maximum power can be fitted in a linear function. But the cathode plot is still undiscernible. Now, as a matter of fact, the plots for cathode area versus other parameters are all not discernible. And so from here, we can say that the cathode area is not a good indicator of power generation. For the anodic area, however, two of the plots have discernible trends: the plot for maximum power and the plot for optimum current. Now for the bottom plots, I tried to remove the circled outliers in a what-if scenario, but still no discernible function or curve could be seen. Now these are the model functions being fitted onto the data. Now from here, we can see that the linear model is a perfect fit, having an r-squared value of 0.95. Now I know that the r-squared values for the second order, third order, and power functions are higher by a tiny bit, but they all resemble the linear model with just a slight curve in the middle, just to be closer to the middle point. This comes to me as an overfit for this particular set of data. Now we don't want an overly fitted curve, since we would want our curve to fit additional data or predict future observations reliably. The linear model is also best fit for the anode area versus optimum current. As we can see here, the models for the second order and power also resembles that of the linear model. Now the third order, however, resembles a real cubic curve, and I would have considered this if the top of the curve had data points too. But since no data points are on the curve, I believe this too is an overfit. So to summarize, the anodic surface area is a good indicator for predicting the maximum power and the optimum current, now as long as the setup satisfies these four criteria. So criteria 1, no modifications are done to the setup. Criteria 2, basic PMC types only. Criteria 3, substrate is natural soil, vermiculite, or whole gland solutions. Criteria 4, external resistance falls within 100 ohm to 600 ohm. So as long as the four criteria are followed, these two line equations can be used to estimate the maximum power and optimum current. And lastly, the cathode surface area is not a good indicator. Now for my recommendations, the greatest problem encountered with this study is data gathering. Since correlational research relies on past studies, it is extremely difficult to find sufficient data points that are close to equivalent enough with one another to find an accurate correlation. If there are no monetary issues, it is recommended to create an experimental design instead. Having an experimental design would allow for controlling of variables, thus ensuring equivalent matching of setups. So this is the end of my presentation. Thank you for listening.